RabbitMQ won this benchmark by a wide margin. If you only stay for the headline, that is the headline. In the same harness, RabbitMQ pushed 274 requests per second, while Kafka landed at 74 and MQTT at 39. That is not close. It is a rout. It was not just throughput. RabbitMQ also held the cleanest P95 latency at about 7.6 milliseconds, while Kafka and MQTT both sat near 24. So the winner was faster and calmer at the same time. Now, the caveat that makes the headline worth trusting. This result came from 48 measured slots across 2 scenarios, 2 payload tiers, 2 concurrency levels, 2 repeats, and the same orchestration discipline. Across Kafka, RabbitMQ, and MQTT. No cherry-picked screenshot gets to decide the verdict. Choosing messaging infrastructure is expensive to undo. A wrong call does not just cost throughput. It leaks into tail latency, retry behavior, incident debugging, and the amount of operational pain your team absorbs for years. The runtime topology is equally direct. One runner drives 3 broker lanes, then writes normalized metrics and trace evidence into a shared artifact surface. Different protocols, same benchmarking contract. The repository is the first proof layer. Under projects/Kafka RabbitMQ MQTT26/experiment runner, you can see the harness, the protocol lanes, the configuration, and the artifacts. Living side by side. That layout makes the benchmark easy to challenge and easy to rerun. Every measured slot follows the same lifecycle. Bring services up, wait for health, run the scenario, emit trace events, aggregate the rows, then write the final summary. That repeated loop is what makes the comparison defensible. The control plane is intentionally explainable. One object owns shell execution, one owns trace logging, the broker lane code owns the protocol-specific probes, and the aggregator converts raw rows into decisions. Nothing important is hidden behind magic. The data model closes the loop. We keep run context, run metrics, trace events, and aggregate rows as separate views, so you can move from a chart on screen back to the exact run conditions that produced it. Now we get to the part that actually creates trust, the code. The goal is not to memorize files. The goal is to see exactly where the benchmark exposes its knobs, records its evidence, and validates each protocol round trip. The shell entry point makes the test dimensions explicit before anything expensive starts. Scenario list, concurrency levels, payload sizes, repeat count, and duration are all visible at the boundary, which means the benchmark is configurable without becoming mysterious. Inside the Python harness, total matrix size is computed upfront and logged before the sweep begins. That sounds small, but it matters. The operator can see progress, ETA, and expected work before the runner disappears into a long protocol loop. Kafka earns trust through isolation and verification. Each run creates its own topic scope, pushes a tokenized message, waits for the matching consim path, and records the outcome. If Kafka is fast or broken, the harness has to prove it with a round trip. RabbitMQ follows the same principle with a different mechanism. It creates a throwaway queue for the run, validates publish and get responses, and keeps the HTTP-level evidence attached to the measurement. That makes failure attribution much easier than a vague timeout counter. MQTT is tested with subscriber-first discipline. The subscriber is waiting before publish happens, the payload token has to come back intact, and the client return codes are logged with the result. That keeps the lightweight lane honest instead of merely optimistic. The trace logger is the forensic backbone for all 3 lanes. Phase events, command events, request events, and response events all land in one NDJSON stream. When a chart looks suspicious, that trace is how you walk backward from summary to root cause. Terminal evidence is the final proof that the run really happened. The artifacts directory shows the result tables, the chart data, the verdict payload, and the tail of the trace stream from the exact execution window. Nothing in this story needs a hand-waved screenshot. Now the scoreboard. In this matrix, RabbitMQ owns the throughput lead by a wide margin. Kafka is a distant second, and MQTT stays well behind on raw output under the same pressure profile. Scaling is where the story gets more useful. RabbitMQ keeps its lead as payload and concurrency change, while Kafka loses ground when pressure rises and MQTT stays comparatively flat. That tells you the winner is not coming from one lucky slice. Distribution is why averages are never enough. RabbitMQ keeps the tightest P95 spread, while Kafka and MQTT show much wider latency variation. A stable median means very little if the tail keeps wandering. The trade-off view compresses the decision into one picture. RabbitMQ sits in the corner you actually want, more requests per second with lower P95 latency. Kafka and MQTT both give up too much on one axis to beat it in this run. The pressure heat map makes the caveat visible. RabbitMQ is consistently strong across the matrix, but the other lanes are sensitive to scenario shape and concurrency. That is why this verdict is evidence-backed, not universal. So the verdict for this harness is straightforward. RabbitMQ wins this benchmark because it combines the highest throughput, the best tail behavior, and the lowest error pressure in the same measured window. The practical guidance is equally straightforward. If your workload looks like this matrix, start your evaluation with RabbitMQ. If you need Kafka semantics, rerun with lane-specific tuning before rejecting it. If simplicity and lightweight telemetry matter most, MQTT can still be the right operational choice even when it loses the headline chart.